All right, ready to dive into some serious quantum weirdness. You sent us an MIT OpenCourseWare lecture transcript on entanglement and Bell's theorem, so I think it's safe to say.
You want to go beyond the basics.
We're going beyond the basics, yeah.
Indeed, it seems you're interested in getting to the practical building blocks of quantum computation.
Yes.
And there's no better place to start than quantum gates and algorithms.
Okay, I'm all ears. Let's talk about quantum gates first. I know that in the classical world we have logic gates, like AND OR and NOT gates that manipulate bits, but how do we manipulate qubits in the quantum world?
It's a great question, and it gets right to the heart of how we control and manipulate quantum information. Just like in classical computing, we have quantum gates that act on qubits, and just like those classical logic gates, we can combine a small set of basic quantum gates to perform any quantum operation we want.
So it's like having a quantum toolbox with different gates for different tasks. What kinds of tools are in this quantum toolbox?
Well, some of the most fundamental quantum gates are quite analogous to their classical counterparts. For example, we have a quantum NOT gate that does exactly what you'd expect. It flips the state of a qubit. If you apply a NOT gate to a qubit in state 0, it changes to state 1 and vice versa.
Okay, that makes sense. So far, so good.
Yeah.
But qubits can also exist in superpositions, right? What happens when you apply a NOT gate to a qubit in a superposition?
That's where things start to get a little more interesting. When you apply a NOT gate to a superposition, it flips the amplitudes of the states in that superposition. It's not just flipping a switch. It's like flipping the entire landscape of possibilities within the superposition.
Okay, I think I'm starting to see how these quantum gates can be used to manipulate quantum states in ways that are impossible with classical bits. But I have to admit, I'm still a little fuzzy on how these gates actually work. Are we talking about physically changing something about the qubit?
You're right to ask that question because it gets at the physical implementation of quantum computation. These quantum gates are implemented by carefully controlling the evolution of a quantum system. For example, if our qubit is the spin of an electron, we might use magnetic fields to manipulate its spin state. We apply these external fields for specific durations to nudge the qubit in just the right way to implement the desired gate.
Okay, so it's like we're choreographing a delicate dance of quantum states using these precisely timed pulses of energy. I'm starting to get the picture, but let's go back to those quantum gates. You mentioned the NOT gate. What other kinds of gates are there?
Well, one of the most important gates for quantum computation is the Hadamard gate. This gate is what allows us to create those mind-bending superpositions in the first place.
Okay, the Hadamard gate is the superposition creator. How does that work?
Imagine you have a qubit that's definitely in state 0. What the Hadamard gate does is transform that qubit into a state that's an equal superposition of 0 and 1. It's like taking that definite state and turning it into a blurry, indeterminate state where both possibilities are equally likely.
So the Hadamard gate introduces uncertainty. That seems counterintuitive. Why would we want to introduce uncertainty into our computations? Isn't the whole point of computing to get definite answers?
That's a great point, and it highlights a key difference between classical and quantum computing in the quantum world. We can embrace this uncertainty and use it to our advantage by creating superpositions. We're essentially allowing the quantum computer to explore multiple possibilities simultaneously, and that's where the real power of quantum computation comes in.
Okay, so the Hadamard gate lets us create these superpositions, which are like opening up a whole new dimension of computational possibilities. What other tools are in our quantum toolbox?
Another essential gate is the controlled NOT gate, often called the CNOT gate. This gate is what allows us to entangle qubits to link their fates together in a way that's impossible in the classical world.
Entanglement. That's the spooky action at a distance stuff that Einstein famously objected to, right? The idea that two entangled particles can be linked even when they're light years apart.
Exactly, and the CNOT gate gives us a way to create that entanglement in a controlled way. It acts on two qubits, a control qubit and a target qubit. If the control qubit is in state 1, the CNOT gate flips the state of the target qubit, but if the control qubit is in state 0, the CNOT gate does nothing to the target qubit.
Okay, I'm following so far, but how does that create entanglement? I need a concrete example.
Sure. Let's say we start with two qubits, both in state 0. We apply a Hadamard gate to the first qubit, which, as we discussed, creates a superposition of 0 and 1. Now, here's the key. We use this first qubit, which is in a superposition, as the control qubit for a CNOT gate acting on the second qubit.
So we're using the qubit that's in a superposition to control what happens to the other qubit.
Exactly. And the result is that we end up with a state where the two qubits are no longer independent. Their fates are intertwined in a way that can only be described by this strange concept of entanglement. They are linked together even if we physically separate them.
Wow. Okay, so with these three gates, the NADI gate, the Hadamard gate, and the CNOT gate, we have the power to create superpositions, flip states, and entangle qubits. That's a pretty impressive set of tools for manipulating quantum information.
It is, and it's these tools that allow us to build quantum algorithms, which are sequences of quantum gates that can perform specific computational tasks. And here's where things get really interesting, because some of these quantum algorithms can perform calculations that are either impossible or incredibly slow for classical computers.
Okay, that's what I've been waiting for. Quantum algorithms.
Yeah.
These are the things that are supposed to give quantum computers their edge over classical computers, right?
Precisely, and one of the earliest and most elegant examples of a quantum algorithm is the Deutsch-Jozsa algorithm. It beautifully illustrates the power of quantum computation by solving a problem that's surprisingly difficult for classical computers.
Okay, I'm all ears. Let's dive into the Deutsch-Jozsa algorithm and see what this quantum advantage is all about.
Let's do it.
All right, so we've got our quantum toolbox filled with gates like NOT, Hadamard, and CNOT. Now let's talk about how we use those tools to build quantum algorithms. You mentioned the Deutsch-Jozsa algorithm as a prime example of a quantum algorithm that demonstrates the power of quantum computing. What problem does this algorithm solve?
The Deutsch-Jozsa algorithm tackles a problem that might seem a bit abstract at first, but it beautifully illustrates the kind of advantage quantum computers can have. Imagine you have a function, we can call it fx, that takes a single bit as input and outputs a single bit.
Okay, so it's like a black box that takes a 0 or a 1 and spits out a 0 or a 1.
Exactly. Now, this function can either be constant or balanced.
Okay.
A constant function always outputs the same value regardless of the input. So it either always outputs a 0 or always outputs a 1. A balanced function, on the other hand, outputs a 0 for half of the possible inputs and a 1 for the other half.
So our challenge is to figure out whether the function is constant or balanced. I guess we could just try both possible inputs 0 and 1 and see what we get.
And that's exactly what you would do with a classical computer. In the worst case scenario, you'd need to evaluate the function twice to be absolutely sure whether it's constant or balanced.
But with a quantum computer, we can do better. That's where the Deutsch-Jozsa algorithm comes in.
Precisely, the Deutsch-Jozsa algorithm leverages the power of superposition and interference to determine whether the function is constant or balanced with just one evaluation of the function.
Wait, hold on. Just one evaluation? How is that even possible? I'm definitely going to need you to break this down for me.
Okay, picture this. We have two qubits. We start by preparing the first qubit in a superposition of 0 and 1 using a Hadamard gate, just like we talked about earlier.
Okay, so we're already using superposition to explore both possible input simultaneously. That makes sense. What about the second qubit?
We prepare the second qubit in a slightly different state. We set it to state 1 and then apply a Hadamard gate to it as well. This creates a specific type of superposition that will be crucial for the algorithm to work.
All right, so we've got our two qubits carefully prepped in their superpositions. What happens next?
Now we apply a quantum gate that represents our mystery function, fx.
Okay.
This gate acts on both qubits, taking the state of the first qubit as input and modifying the state of the second qubit accordingly.
So it's like we're feeding our superposition of inputs, both 0 and 1, into the black box simultaneously.
Exactly. And because of the way we've prepared the second qubit, the output of this function gate encodes information about whether the function is constant or balanced.
Okay, I'm starting to see the glimmer of something amazing here. We've essentially evaluated the function on both inputs at once using superposition. But how do we extract the answer?
Here's the ingenious part. We apply another Hadamard gate to the first qubit.
Okay.
This sets up an interference pattern. Think of it like waves on a pond. If the waves are in sync, they reinforce each other, but if they're out of sync, they cancel each other out.
So we're using interference to amplify the signal we're looking for.
You got it. And finally, we measure the state of the first qubit if we measure state 0. We know with certainty that the function is constant. If we measure state 1, we know it's balanced.
No way we've determined the nature of the function with just one evaluation. That's mind-blowing. We've essentially bypassed the limitations of classical computing by exploiting the unique features of the quantum world.
Precisely. The Deutsch-Jozsa algorithm, while dealing with a seemingly simple problem, demonstrates the incredible potential of quantum computation. It highlights how we can leverage superposition and interference to perform calculations that are impossible or far slower for classical computers.
This is just the beginning, right? I can only imagine what kind of complex problems we could solve as quantum algorithms become more sophisticated.
You're absolutely right. The Deutsch-Schotze algorithm is just a glimpse into the vast landscape of quantum algorithms that researchers are developing. And as quantum computers continue to improve, these algorithms have the potential to revolutionize fields ranging from medicine to material science.
Speaking of revolutionizing our understanding of the universe, I can't help but think back to that spooky action at a distance we talked about earlier, entanglement. It's such a bizarre concept, and yet it seems to play such a fundamental role in quantum mechanics. Is there any way to know for sure if this is really how the universe works? Is there any way to test whether entanglement is really as strange as it seems?
That's a fantastic question, and it leads us to one of the most profound insights in the history of physics, Bell's theorem.
Okay, Bell's theorem. I'm ready for another deep dive. Let's hear it.
Mm.
Okay, my mind is still reeling from that Deutsch-Dose algorithm. It's amazing to think that we can leverage quantum phenomena to perform calculations in ways that classical computers can only dream of. But now I'm really curious about this. Bell's theorem, you mentioned, it sounds like it tackles the very heart of what makes quantum mechanics so strange and counterintuitive.
Bell's theorem is indeed one of the most profound and mind-boggling ideas in physics. It addresses the question of whether the spookiness of entanglement, that apparent instantaneous connection between entangled particles, is a genuine feature of reality or just an illusion arising from our incomplete understanding.
So it's like asking, is the universe truly random and interconnected at its core, as quantum mechanics suggests? Or is there some hidden deterministic mechanism that we just haven't figured out yet?
Exactly. Bell's theorem gives us a way to experimentally test this question. It all boils down to a testable inequality called appropriately enough. Bell's inequality. This inequality sets a limit on the correlations that can be observed between two particles if their behavior is determined by local hidden variables.
Local hidden variables, what are those?
Imagine that each particle carries with it a set of hidden instructions that predetermine its behavior even when it's separated from its entangled partner. These instructions would be local in the sense that they're attached to the particle itself, and they'd be hidden because we can't directly observe them if such hidden variables existed. They would explain the correlations we see between entangled particles without resorting to spooky action at a distance.
So it's like saying there's a secret code embedded in each particle that tells it how to act, even when it's far away from its entangled partner. And Bell's inequality tells us whether this secret code is even possible.
Precisely. Bell's inequality sets a boundary if the universe is fundamentally classical, meaning it operates according to local hidden variables, then the correlations we measure between entangled particles must obey this inequality.
Okay, I'm following so far. Bell's inequality draws a line in the sand, saying if the universe is classical, the correlations can't be stronger than this. But what happens if we do an experiment and the results cross that line? What does that tell us?
That's where things get really interesting. If we observe a violation of Bell's inequality, it means that the universe cannot be explained by any theory that relies on local hidden variables. It would be a resounding confirmation that the universe is fundamentally quantum mechanical with all its weirdness and non-locality.
So we're talking about an experiment that could potentially settle one of the deepest philosophical debates in physics. Has anyone actually done this experiment?
Yes, in the early 1980s, a physicist named Elaine Aspect conducted a series of groundbreaking experiments that did exactly that. He measured the polarization of entangled photons, particles of light, and found correlations that violated Bell's inequality.
So Aspect's experiments provided compelling evidence that the universe is truly governed by the bizarre rules of quantum mechanics, that the spookiness of entanglement is real.
Exactly. These results have had profound implications for our understanding of reality. They suggest that the world is not a collection of independent objects with predetermined properties, but rather a deeply interconnected web where entanglement plays a fundamental role.
Wow, it's both unsettling and exhilarating to realize that we live in a universe that operates according to rules that defy our everyday intuition.
It truly is, and while the implications of Bell's theorem and Aspect's experiments are still being debated and explored, they have undoubtedly opened up new vistas in our understanding of the universe and paved the way for the development of revolutionary technologies like quantum computing.
Well, I have to say, this deep dive has taken me on a wild ride through the quantum world. We've gone from the basic building blocks of qubits and quantum gates to the mind-bending concepts of superposition entanglement and Bell's theorem. It's clear that quantum mechanics is not just a theory. It's a description of a reality that is stranger and more wondrous than we could have ever imagined.
I completely agree. And the most exciting part is that we're only just beginning to explore the vast potential of this quantum realm. Who knows what incredible discoveries and technological advancements await us as we continue to delve deeper into the mysteries of the quantum world.
I, for one, can't wait to find out, and to our listeners, thank you for joining us on this quantum adventure. We hope you've enjoyed the journey as much as we have. Until next time, keep exploring the wonders of the universe, both big and small.